Okay, so hey guys, today is the day 11 of our Leetcode daily until I get a job. So let's get started with the questions. And yeah, okay. So these are the six questions we'll be doing today. All the medium questions we will complete, and if we have time, we can do more further questions also. So let's start with the first question, which is the lowest common ancestor of a binary search tree. So as we can say from the name that we are given with two nodes, like here we are given with P and Q. These are the two nodes of this tree, and we have to find the lowest common ancestor of this. Ancestor means the predecessor, means our fathers and forefathers, like as we say ancestors, who are our ancestors, दादा परदादा होते हैं वही होते हैं ancestors. तो हमें देखना है कि 2 और 8 का सबसे लोएस्ट कॉमन एंसेस्टर क्या है, मतलब सबसे रीसेंट वाला एंसेस्टर कौन है. जैसे यहाँ पे 2 and 8 है, इसका सबसे कॉमन क्या है, 6 ही है. इसके ऊपर तो कुछ है भी नहीं वैसे भी. वहीं पे अगर 2 और 4 हम कह दें, अगर 2 और 4 का सबसे लोएस्ट कॉमन एंसेस्टर खुद 2 ही है. क्यों? क्योंकि द लोएस्ट कॉमन LC ऑफ नोड्स 2 and 4 is 2, since a node can be a descendant of itself according to the LCA definition. So just look for the LCA definition on the Wikipedia. Lowest common ancestor of two nodes V and W in a tree or directed acyclic graph is the lowest node that has both V and W as descendants. Okay, and where we define each node to be descendant of itself. So यहीं पे अगर देखो एग्जाम्पल के थ्रू देख लो कि जैसे 2 और 8 का तो 6 है, 2 और 4 का 2 है, लेकिन वहीं पे अगर हमारा ऐसा होता है कि हमें 0 और 7 का निकालना है, तो 0 और 7 का लोवेस्ट कॉमन एंसेस्टर कौन सा है जिससे दोनों हम डिराइव कर सकते हैं. 2 है, नहीं 2 से 0 पे जा सकते हैं लेकिन 7 पे नहीं जा सकते. 8 है, नहीं 8 से 7 पे जा सकते हैं लेकिन 0 पे नहीं जा सकते. सिमिलरली 6 हो सकता है. क्यों? क्योंकि 6 से 0 पे भी जा सकते हैं और 7 पे भी जा सकते हैं, और ये सबसे लोवेस्ट यही है. राइट. वही हम 3 की बात करें और 0 की बात करें, तो 3 और 0 का लोवेस्ट कॉमन एंसेस्टर कौन सा है? 2 है, क्योंकि 2 से हम 0 पे भी जा सकते हैं, 3 पे भी जा सकते हैं. इससे पहले, इसके बाद में ऐसा कोई भी एलिमेंट नहीं है जहाँ से हम दोनों जगह जा सके. 4 से हम 3 पे नहीं जा सकते, 3 पे जा सकते हैं पर 0 पे नहीं जा सकते. राइट. तो इसलिए 2 हो जाएगा. सो इस तरीके से हमें देखना है. और एक और तरीका है इसको विजुलाइज करने का, वो हमारा ये हो सकता है कि जैसे अगर हम ये देखें कि ये हमारा रूट है, ठीक है, एंड इट्स अ BST. कीप इन माइंड इट्स अ बाइनरी सर्च ट्री. Binary search tree is basically, what is a binary search tree is that the left element will be smaller than, the left node will have a smaller value than the root value, and the right will have a larger value than the root value. So it is what a BST means. Okay, so we have two of these nodes, right? Now they can have further, there are more nodes. Let's say this is the tree. Okay, so if we have two, and let's say it has two more nodes. For a better example, let's consider this case. And now let's say our P is this and our Q is this. For these two nodes we have to find the lowest common ancestor. Now we will start at root, and we will see, what we want to see is that are the both elements on the same side of the root or on the different side of the node. Because whenever we will get the condition where both the elements are on the different side of the root, this is our LCA. That will be our LCA, lowest common ancestor. Okay, but when we know that both the elements are on the same side of the root, like this is the root, both the elements are on the left subtree, right? So we know that there is further, we can go further down on the left side. Right side has no involvement in this, so we can go further left side. We will come here now, roots left. Now we will see, are the both elements on the same side or different side? They are on the different side, right? Like we can consider like this, that let's say this is my grandfather. He has two sons, 1 and 2. Okay, but let's say this is me and this is my brother and this is my father. I am a son of 1, okay, and 2 is my uncle. Okay, so when we try to find the lowest common ancestor of me and my brother, let's say these are this is my brother and this is me. So what will be the lowest common ancestor of me and my brother, to whom we both are related, and he is the most recent relation? That will be our father, right? Our father is our lowest common ancestor. So when we go to our grandfather, we know that we will start our finding at our grandfather. Okay. Now we know that we both have the same father, and so that means that both of us, like me and my brother, will exist only on the this side of it, one side, not two side, right? So that's why we will come on this side, and when we will see that it's our father only one, and he is our lowest common ancestor, we will pick this as the answer. Similarly, in the BST, left side is smaller, right side is larger. So we will see that if both the P and Q are smaller than that, or we can say, we just have to find one thing: if they exist on the different side or on the same side. If they exist on the same side, we will go further on that side. They exist on left, we'll go further here. Now we will check they are on the different side. Yeah, so this is the answer. That's what we need to do. So there's a lot of ways to understand this question, but that's the most simple way we can understand this. So let's just write down the code here. We just have to find out the condition when both the elements are on the different side. Okay. So how do we know that they both are on the same side or different side? One thing we know for sure is that this value, let's say V, is larger than V1 and smaller than V2 because it's a BST. So to check, like this is A, okay, this is A, P and Q. Okay, P and Q, let's have values P and Q. It has value P, it has a value Q. Now how to check if they both exist on the same side of this V or not? So we know that V is greater than P and V is greater than Q also. So V minus P is a positive number, right? And V minus Q is also a positive number. So if they both are positive, their product must be positive, greater than 0. So if the product is greater than 0, this will mean that they are on the same side, right? Even if they are both were on that side, then what will happen is we will be less than P and we will be less than Q. If the P and Q are both on this side, then this will be negative, this will be negative, but the result will be positive, right? So this means that whenever this result will be positive, they both are on the same side. And when this is less than 0, they are both on the different side. So we'll go according to this condition that while the product of what, roots value minus P's value and this product with roots value minus Q's value, if this thing, this whole product is greater than 0, while this is greater than 0, we have to go into the loop. Okay, we have to stop where this is less than 0. So that will be our stopping condition. So this condition will work that until this is true, we will go on, we will try to search it. But on which side we need to go now? We need to go on the left side or the right side. So we will check now that if the roots value is greater than P's value, so P is smaller, right? So if P is smaller, it is existing on the left side of this root. Okay, if this is the case, then we will go to the roots left, else we will go to the roots right, correct, and we will just return the root. So this will work. Yeah, correct. So we'll just submit it. Wait a second. It's overflowing, right? This and this, P is this, Q is this. Then what we can do in this case when the value is overflowing, have we do we have any other way of calculating, like how we can approach this? Mm, we need to find that if they are existing on the same side or the different side. Okay, that's all we need to do. So what we can do here is mhm. I guess mhm. Okay, wait. Yeah. So how we can find that they're on the same? This will work, but how many tasks is passed? 28 tasks is passed. Obviously, it's now overflown. So we have to find some other way of doing this. Like this is a correct approach, but not in the case of larger inputs. So in the case of larger input, we need to find some other approach here, and that could be like we have this, and what approach could we take here? We have to take something where we do not have to like find the products or product of the two values. We can compare the two values but not the product, because it will overflow the limit of integer. So what we can do is that if hmm, let's say we are here. Okay, we have to find the lowest common sister for these two. We are here and we are here. Okay, so we will try to find the answer on the, we are here. Okay, and we have to find for these two. So we will go to left as well as we will go to right. Okay, let's say we'll go to left and we will go to right. So when we go to left, we'll go further left. Cool. Now we are here. When we are here, we will see that this is one of the values we need to find the ancestor for. So it will return from here. It will return from here. It will return the root. If this is one of the values, if root's value is p or q, then we will return the root, right? We know this condition that when the when the value is when the value is the LCA itself, if any of the value we get to any of the value which is equal to itself, then we will return it, right? If we get to 2 and it is one of the value we need to find the ancestor for, then we'll return 2. Okay, so this is basically will be a, you can say, a recursive solution that will go to the leftmost. We will check if this is the value we need to find the ancestor for, we will return the root, we will return p for this. So its left answer has something. Then we will go to the right of it. Right, we find the value again. So we will go here. So whenever any root node have, okay, whenever any root node have solution on the both the sides, like left side also, right side also. Like if we do for this value, we will find a solution only on the left side because both the values are on the left. So only left will have a solution, but we won't find anything on the right. So this cannot be the solution. But here we can find both the values on one on this side, one on this side. So it will be the solution. Okay. So it's basically the similar thing, but what we need to do is that there will be two solutions, 3 naught star left, which will be equal to basically the same function we will call, and we will call it with roots left. We will go as left as possible. Okay, with p and q in it. And whenever we find the value equal to, if we find that roots value equal to uh, equal to p's value, or root value equal to q's value, we will just return the root. Okay, so that way we will get an answer for left. Like when we are on 2, when we are on this, we'll get an answer for this side, that left has something. And similar thing we will do for the right. And if both of them have a solution, like left and right are both are not null, so it will go to the right side, and this variable will be called right. And what if we find nothing? We will just return null. Okay. Okay, so let's see. देखो, when we go on this side, we will find a solution for this. Okay, when we go to the right side, it will go here. Is it equal to any of the values? No. P or Q? No. It will go. It will see that we will go to left. We will go to right. Both are null. It will return null, null. This will have both the left and right answer as null. This will have the right answer as null. Okay, if both are not null, we will return true. See, if left is not null and right is not null, both are not null, we will just return root. Okay, and if left is not null, we will return left, else return right. Yes, if left is null, not null, we will return left, and else if left is null, we will return the right, whichever side is not null. Okay, in this case, when we are at 6, we'll go to left of it. We found a solution for the left side. Then we'll go to 2, then we'll go to 0. 0 is not of them, so it will go back. It is getting null from here. From this side, 2 is getting null. Then 2 will compare itself. Like, is it a value? Is it something which we need to find an ancestor for? Yes, it is. Then we will just return the root 4 to 6 that we got 2. On the right side, it will find nothing. On the left, we have found 2. And if 4 will be there, obviously. Both the values must be there. If it's not on the right, it will be on the left, down side of 2. So yeah, we will get a solution for 6 on the left. Does not get a solution for the right. And but we will have to go lower because we have to find the lowest common ancestor. So we will return 2 from here. Okay, 2 will be returned from here and 2 will be the final answer. So this should work. Oh, return capital null. Okay. Wait, root value is equal to p's value or q's value. It will return root. For the left, we'll go to left. For the right, we'll go to right. And if both are not null, we'll return root. If left is not null, we return left. Not else. We just do this. Now we are getting wrong somewhere. Our output is 8. Okay. No. How is it doing this? We have to find 2 and 8, and it's just giving us 8. So it is giving, whenever we find this, we are returning it. No, it should not be happening actually. What should be happening is if we have this value, roots value as equal to p's value or q's value, will return the root. And then we have to answer left and right. If left is not null and right is not null, left is return left, else will return right. How can if we consider this root PQ, if not of root, if root is null, we will just return null. Okay. Root left, root right, left and right answer. Right, and if left is not null and right is not null, we will return root. If left is not null, we will return left, else we will return right. This is correct. I mean, where is this failing? PQ, PQ. We'll go to left. It will go to 2. Then it will again go to left. It will go to 0. No, it will go to 2. Okay. When we go to 2, we'll see that its value is equal. So we'll just return root. It will return the root. Root is 2. It will return the 2 for this. Left has we have got something. Then we'll go to right of 6. It should return 6, man. Because when we go to right, it will go here and check if its value is equal to q dot value. When you go to right 8, right? Or q dot value, it will return 8 here. And so we have the right answer as well as we have the left answer. So it should return, if left is not null, right is not null. Right, we have something for both. This is just wait a second. Left where and right well. Left well, right well. If we run it, oh, this is not cool, man. This would take LNR. These are keywords, man. Okay, these are keywords basically, so we cannot take the LNR like this. Okay, just say that if L is not equal to null, then this, else empty, L empty. Okay, let's try this like this. And if R is not null, then this, else R empty. Okay, we will do this. Is this fine now? Let me just do this, and let me just do this. You run it. Okay. Okay. So our output is 2 and 8. We have left as well as we have right. So why is this given it 8? It should be root, right? So let's see. L is not null. If we write like this, will it work? And let's say let's copy this method for all of them. Okay. Yeah. There's no way that this is the error. Exactly right. Root is not null. Return null. If root is null, oh fuck. What the fuck am I doing? What the hell, bro? Sorry guys, sorry. Okay. It took a lot of time, man. It shouldn't have took that much time. Okay. How much time did it take? Oh fuck, 27 minutes. Okay, no worries. Level loader traversal, it's basically easy. We can apply the BFS here. That we will just take a, let's say firstly we will take a vector of vector int as the answer. Then we will take QE. It will contain the tree node star and it will contain Q. It will be Q, okay. And what we will do here is that if root is null, we will just return the answer right here, okay. Else we will q dot push root. Now while q is not empty, we will do what is, we will calculate the size of this q, okay. Okay, we will calculate the size of this q, and we will take a vector int, let's say temp, and while as z minus minus, we will run a loop for this, and tree node star temp node is equal to q dot front, because the element is inserted from the back and discarded from the front of the queue, okay, popped basically. And then we will just q dot pop and temp dot push back the value of what, the temp node, okay. And if temp node has a left, we will just q dot push temp node's left, and we will do the same thing for the right, okay. And once we complete this, we will just answer dot push back temp, and we will return the answer, right. Yeah, it's done. Next is count the good nodes in the binary tree. Given a binary tree is root, a node x is named as a good if there is a path from x to root to x and there is no nodes greater than the value of x. Okay, so we are starting from the root to that node, and up to that node, if there is no value greater than current node, then it is a good node. Okay, this means the root node is always a good node. Okay, the number of good nodes. So like this, 3 is a good node because it's a root. We'll go to 1. Is there any value greater than 1 in this path? Yes, 3 is greater. If there's any value greater than 3 is the path, yes, the greatest value is equal to it, so it will be also a root node. It is 4 is also, 5 is also. Yeah, okay. So what we can do is, what is the maximum value for any node? The constraint is 10 to the power minus 4. So we will just call out a helper function, and helper will pass out the root and the minimum possible value, that is 10 to the power minus 4. Okay, we'll declare the int of count 0 as a global variable, and we will do this train out star root and int max अब तक का maximum. ठीक है. So if the root value is greater or equal to the max, then we will just do the count plus plus count count plus plus count. Okay, count plus plus, and the second thing we will be doing this max will be equal to root's value. Okay, and we will do this for basically help of roots left and not max, let's take it maximum, because max is a keyword basically, so that's why it will be a bad choice of letters. Helper for roots right node and maximum we provide here, right? And we will return the count here. Perfect. Let's see within a null. Okay, if the root is null, we'll just return it. Perfect. If the root is null, we will just return. Okay, perfect. Validate the binary search tree. So validating the binary search tree has a lot of methods to, we have a lot of methods to validate the binary search tree basically, but the method we will be taking is the most simple to understand and like the most layman approach we will take. That is, what is the maximum and minimum value for this? The maximum value this node can take is less than 2, just less than 2, and the minimum value it can take is anything in the constraint, and we have the constraint as 2 raised to minus 31, so we have to take the long here. So we will call out a function that is return helper. We will provide the root and we will provide the minimum possible value and maximum possible value for the current node. Okay, long min and long max are the minimum and maximum value for the current root node. Okay, now we will do this helper train out star root and int maxi int minimum value. Okay, so what we can do here is that if yeah, if the root is null, we will just return true, right? If it's empty tree, it's true, it's BST. And if the root's value is less or equal to mini, or it's greater or equal to maxim, then we will return false. Even at the equal, because this value 1 cannot be equal to 5. Okay, it should be less than 5, not equal to 5, otherwise it's not a BST. And we will also return helper for roots left. And now roots left will have what constraints? Minimum will be the same, but will be the maximum. Maximum value for the left will be roots value, and minimum will be the minimum we have earlier. And both must be true, right? And helper roots right will have constraint as maximum will be, maximum can be anything and minimum can be root value. Correct? And I think it should work. Alpha function root right, okay. It's giving a wrong there. It's returning the false. Is helper null is true, roots less than minimum, or it's a greater or equal to maximum. Correct. So we will go with 2. 2 can have anything. 2 has a value greater than minimum, right? And it's less like this condition is not true. It's less than minimum, no it's not, false. And is it greater or equal to maximum? No, it's not. So it will go go here. We will return what? Helper for 1. 1 is the left value. 1's maximum value should be second as the maximum. Okay, maximum value should be roots value, that is 2, and minimum can be anything. And for the right, roots right, maximum is the maximum value it can have, and minimum is the roots value. It's correct. I mean, what's the problem here? I don't see it. Long max and long minimum are the yeah, I guess this is the way to declare them. Then what is the problem here? If the root is not root is null, we will just wait. Let's do this. It's not int, it's long. Might be, but I don't think this should be the problem. But it can be. Yeah, it was the problem actually. So yeah, this is the good approach and correct approach, and that's an easy approach to understand, obviously, and it's a good time complexity also. So kth smallest we have to find. See, kth smallest in a BST. So about a BST, there's a fact. There's a fact about BST, which is that the in order traversal of a BST is in ascending order. Okay, if we traverse this BST in order traversal, through in order traversal, it will return us a ascending order array of its values, like 1 2 3 4 will be the output of this tree. Okay, so we can use this fact. We can use this fact to calculate to find out the answer to this, but we will not do like we will do in order traversal. We will output an array from that, and from that array we will take the kth element. That will not be a good approach, because that will take a extra space, obviously, and we don't want to use the extra space. We just want to traverse it once in ON, and we just want to find out the k smallest. Okay, so what we can do is here is that we will be traversing it with the only like in order, but we will not be storing the elements in an array. We will just keep track on which numbered element we are. Like on 1 we are at first element, on 2 we are at second element, on 3 we are third element, like this. We want to keep track of this only. Okay, will not be storing the values in an array and then returning that value. Okay, so let's say we will be having these two values. You will see why we are using these values. And what we can do is we can call out the helper function for root K A B. Okay, and we will just return B here. Okay, and why are we doing this? You will get it. Just let me write the solution. Helper tree node star root and K, and A and B will be referenced by values. Okay, referenced by values. They will be taken as references, not the direct values, because we are saving them actually. They must be same in every function code. They will be saved for every function code. Okay, so if the root is null, it will just return it will just return. Okay, now whenever then we will call the function for the left, because in order, what is that in order? Left, then the root, then the right. This is the in order. Okay, so we'll call it for left, so that we can go to the leftmost element first. Okay, and then K, and then A, and then B. Now when we are at the leftmost element, means we are at 1, we'll do what? A plus plus. We will do this A plus plus, and if we are storing the element now, and if K is equal to A at any time, then the roots value, we will store the roots value in B. Now we have the kth smallest. Okay, and after that we will helper root right K A B. Like, it's pretty easy to understand. I guess there's nothing which we cannot understand in this approach. We are tracking, we are just keeping track of on which element we are according to the in order, and when we are the kth element, we will save this element and return it, because the kth element in is smaller, because the in order traversal of a BST is ascending order array of the values. So that's why we did it, and it's perfect. Construct a binary tree from pre-order and an order traversal. So that's a pretty much like very famous question, and it's a very good question. Why is it so? See, here we are given the pre-order traversal of this tree and in-order traversal of this tree, and we know that pre-order traversal of the tree gives us what? The first element of the pre-order traversal is the root of the tree. Okay, so here we have 3, and if we try to find 3 in the in-order traversal, we got it here. So whatever is on the left of this left of 3 in the in-order array, it's in the left subtree, and whatever we have on the right side of in this in-order traversal of 3, it is in the right subarray, right subtree of 3. Okay, so we need to use this fact only, and we can do this. So um, so we will just return, let's call a helper function, and do the like pe and in order and pre-order. This to make them small and easy. So pe ie. What are the indices? So 0 to pre-order dot. That's all we need to have. Okay, -1, -1, and in order start is 0, and ie dot size -1. Okay, I'll remove this off. Okay, now we call the helper function node star helper. These two vectors we will be having, right? Then the values like pre-order start, pre-order end. No, let's just take it p and I. Okay, p and I, p and I. So int pre-order start, pre-order end. So oh guys, wait a minute, someone has arrived at my home. Okay, so where are we? Yeah, period start, period end, and then the next will be in order start and in order end. Okay, so what we need to do here is now, if pre-order start is greater than pre-order end, if pre-order start is okay, we will be considering this. No, let's firstly make the root element will be our root value of root element will be what? This will be pre-order start p dot ps, right? This will be our root element, and let's consider this variable, and let's run this for loop to find where this root value exists in order, and on the left is the left subtree, on the right is the right subtree, so that way we can do. So for I is equal to in order start to I is less or equal to in order end I plus plus, and if in order I, okay, man, let's say in, okay, in order of I that is equal to root, at that time we will break. Okay, so we have this position now, so let's create a root node is equal to new tree node, and let's insert the value inside it. So we created a root node. Okay, now what will be root nodes left will be what? Not root node, it's actually root nodes left will be, we will call this function helper for p and I in. Now in order start will be, sorry, pre-order start will be pre-order start plus 1, because the first element is the root of it, right? And the end will be, see now how will we consider this end, is the number of elements before 3, that is 1. After 3, the number of elements, this much elements are in the left subtree and the rest are in the right. So we will only have to have this length of elements on the right of 3 in this array, on the right, on the left subtree, right? So we will do what is pre-order start plus I minus in order start, that is I, this is I, and this is the in order start. So 1 minus 0 1, so we have to only go one element further, and we will have all the elements of left subtree for 3. Okay, and what will we do for the in order is that in order start to in order I minus 1. Okay, I minus 1, I is 1, 1 minus 1 0. So yeah, only this element is here, 0 to 0. This element will be on the left subtree. On the right we will just copy it, and right subtree will be p in. So this will be this value plus 1 to post or pre-order end. Okay, ps plus I minus in order start plus 1 to pre-order end. Okay, and this will be I to in order end, right? I plus 1 actually, because I is the current node, I end. Okay, and we will just return this root node. Yeah, exactly. And now where we have to start, where we have to stop, we have to stop when we have to find some condition with the help of these indexes only. See, for in order See, okay, for in order we are just going further and further, for but for in the pre-order array we are doing this, right? So if our pre-order start is less than, sorry, is greater than pre-order end, then we will return. At that moment we will return. Let's see if this is correct. P dot size, p dot size, no, no, it's p dot size and I dot size. Correct. Yeah, it's done. So these were the 6 questions. On the first question, we took a lot of time, but that was because we were doing some silly mistake which we were not able to catch up. So that's fine. And right now we have like 52 minutes. Okay, 52 minutes video we have done. And okay, that's fine. We have all the medium questions of tree as well. And now we will be doing is tomorrow we'll be doing these two hard questions actually. Serialize and deserialize binary tree and binary tree maximum paths. So these two are also good questions. So we'll do them tomorrow and we will be done with the tree of this list. And then we will pick up some other list. Okay, and we will continue to, but no, we will continue to do only this sheet. Let's finish this first. The next topic will be graphs. Okay, so yeah, that's it for today. We'll meet on the day 12. Bye, guys.